draw this graph in the other blackboard in the larger size. Because as I said, I need to put the rainfall here, and I need a larger sketch. Now, just for the sake of introducing an example, I draw a curve here, a generic curve. Okay, so let's also remember, take into account that T is cumulative rainfall from the beginning of the event. And this is, in units, it's expressed as length over time. So it's not a flow of rainfall. It's rainfall, let's say height, rainfall depth, divided by the time in which it occurred. Let me think if there is time or not. No, there is no time. Sorry. It's just rainfall depth. Because I have to put it here in this abscissa, so I need the same unit. Now let's suppose that at a certain time we have a rainfall P star. Or let me call here PT, it's fine. I don't need to. And as I said, I can identify this rainfall value over the abscissa because it's the same unit. I can put it there. And let me make a premise. This model, because you may wonder if it's net rainfall or gross rainfall. So this model, you will see later, includes an evapotranspiration component. So what I'm depicting here is gross rainfall. Okay, so it's not net rainfall. I don't need to introduce a runoff coefficient here. It's gross rainfall, pioggia netta in Italia, pioggia lorda in Italia. And for now, I'm not considering evapotranspiration. I will introduce evapotranspiration later because it's a complication. For now, let's suppose that it just rains and I have no evapotranspiration. Okay. So basically, if you want to get an estimate of the total volume of rainfall, keep in mind that this rainfall is assumed to be uniform over the basin. So uniformly distributed in space. So at time t, what is the volume of rainfall that occurred over the whole catchment is given by this whole area here. It's P times 1. Okay? You may say that this is not the area of the catchment, but it is indeed, because it's a percentage of area, so of course you need to introduce, if you want to get the real volume, you have to introduce the catchment area. But we made the assumption before that we refer to the area in percentage terms. So let me say that this is, let me say in an approximate way, in a colloquial way, that this is the volume of rainfall. Okay? Of course, if I had depicted, if I multiply here the percentage times the area, I get the real volume. But this is, in any case, the specific volume of rainfall. To be rigorous, it's a specific volume of rainfall of the catchment. Now the question is, what part of the rainfall is stored and what part of the rainfall is transformed in runoff? First, let me reformulate the question, because this is, let's say, the last conceptual point that is difficult to understand. So my question is, given that this area here is is proportional to the total volume of rainfall over the catchment, what is the part that is stored in the catchment, and what is the part that is transformed in runoff? What is the part that is forming the river flow? Now, to reply to this question, let's just remind to all of you, to all of us, that if this curve was given by beta tending to infinity, we will get an impervious catchment. Of course, in an impervious catchment, everything is transformed in river flow. Conversely, if I have the opposite situation, where the curve is lying on the abscissa, I would get a catchment that absorbs everything until the rainfall reaches the maximum storage. So, if the curve was just lying over the abscissa, I wouldn't have any river flow. If the curve is lying over the ordinate, then I would get everything transformed in river flow. So let me just to anticipate intuitively that the area that goes here, the area that is below the curve is the river flow, is the runoff. And then we have to prove it, okay? But intuitively, I think that I explained to you already the result, which means that, what is that? What is that area? Is the integral of this relationship between 0 and pt. This area that I marked here, below the curve, is the integral of the relationship of the curve itself between the extremes 0 and pt. So basically, I already anticipated the result, and I already anticipated that to estimate the river flow, I have to complete this integral here. And this is why I said this is a relationship that is easy to integrate. But now let me try to explain a bit better why this area is giving an estimate of the runoff. And in order to give this explanation, let me concentrate on a small interval delta p. This interval here, let me color it, to which we can associate with good approximation a constant value C star. C star, never used before, no. Okay, so of course this area which I marked in white, which if we are right represents a contribution to surface runoff, this area is given by the product delta P times C star. So let's see what is this product. First of all, delta P is an increment of rainfall, fine. Okay? So it's an increment of rainfall that I get here. And what is C star? C star is the percentage of the area that has a storage capacity that is lower than the cumulative rainfall when delta P occurs. What this means? Let me state again. What is C star is the percentage of the area of the catchment that has a storage that is lower than the cumulative rainfall from the beginning of the event to the instant in which delta P occurs. Let me say again with different words. It's the percentage of the area of the catchment which is saturated when delta P occurs. Because if it has a storage capacity that is lower or equal than the cumulative rainfall from the beginning of the event, this means that this area is saturated. Because the rainfall that occurred up to now is greater than the storage capacity. So this area is saturated. It's like an impervious area. Therefore, if I compute the product, delta P, rainfall in this time step, and I multiply this rainfall for the area of the catchment that is saturated, I get the runoff. So this white step is indeed runoff. And I can prove the same for every other piece of this bigger area which I marked with crosses. So indeed, I mean the area below this curve is river flow. And I have to compute it. If I compute this area, I can estimate the cumulative river flow from the beginning of the event. And of course, if I repeat the same computation for different times, I get at each time step the cumulative rainfall, and by differencing the the cumulative river flow, and by differencing the incremental river flow, which is what I'm looking for. Okay, let's compute this area. It's just given by this integral here. And in order to use the same computation that I'm showing on the slides, let me compute not just the integral alone, but rather the cumulative storage at time t in the catchment. And in order to get the cumulative storage, I just have to take the rainfall and subtract the runoff. So the cumulative storage is Pt minus the integral here. And the integral is computed by from 0 to Pt. Look here. And then let me rewrite this. 1 minus C divided C max to the power of beta in the C. That's it. This is what you find on the slides. And now let me move forward on this blackboard here. Okay. Now, in order to make it simpler, let me compute, because now the problem is to compute this integral, and it requires some steps. And in order to make it simpler, let me just compute it, and not to repeat every time Wt is equal to Pt minus this. Okay? So let me just compute the integral there, and therefore I can say that I rewrite it, integral between 0 and Pt of, I forgot to take it out there. Okay, let me try to move forward with this one. This one. Integral of 1 minus C divided C max to the power of beta in the C. And this is equal to integral between, this is, I can decompose the integral of the sum in the sum of the integrals. So I can write that this is equal to integral between 0 and the pt of dc minus integral between 0 and pt of 1 minus c divided c max to the power of beta in dc. And then this is equal to the integral of dc is just c computed between the extreme 0 and pt minus. And here, the integral is, let me write it, and then, you know, I'm not a good mathematician, so the way in which I compute the integrals usually is by guess, or by memorizing them, and then when I write down the integral, then I compute the derivative and I prove to you that it's fine, okay? This is the non-mathematical way of computing the integrals. In this case, this is an exponent. It's something that is elevated to an exponent. So the integral is C max divided beta plus 1. I think there is a minus here, but then we will check. And this is multiplied by minus C divided C max to the power of beta plus 1. And this is computed between 0 and pt. Yeah, finally I found them. Okay, let's see if it is correct. Let's compute the derivative here. The derivative is beta plus 1, which is eliminated by the denominator that I put here. Beta plus 1, which multiplies the argument of the power, and the power goes from beta plus 1 to beta. So I get here, that's fine. And then I have the derivative of this, which is minus 1 divided c. So if I put it here, it goes back to the original form. I think it's fine. Okay, now let me delete this. And I can write that pt, this is the first integral, the first computation here is just pt minus 0, so pt. And here I have minus, okay, let's compute it, minus, okay, first of all, let's substitute c with pt. And it becomes minus C max divided beta plus 1, which multiplies 1 minus pt divided by C max to the power of beta plus 1. And then I have to put a minus here, and I have to substitute C with 0. So if I put a 0 here, this becomes 1 to the power of beta plus 1, which is still 1. And therefore, the minus becomes a plus and becomes C max divided beta plus 1. I think this is what comes out. The signs are the trouble here. This is a kind of demonstration of proof, in this integration, which I could ask you at the exam if you are a good, if you perform well. Usually this is not the first question, but if after the first question I see that you are performing well, I may ask this. And because it means that you are good, and therefore, you know, I try to ask the difficult question to give you a good mark. And usually when students get in trouble, and when myself I get in trouble when developing it at the blackboard, is because of the signs. So be careful of the signs, okay? And I'm not sure they are correct now, but we will realize if they are not. With the next step, we will realize it. Okay, so let's... the problem with the blackboard is that if I make a mistake after I have deleted, then it's a problem for me to go back. But anyway, let's hope that I didn't make any mistake. And then here we can write PT minus. Okay, so in this case, I can, you know, there is a common factor, Cmax divided beta plus 1, so let me put it here, Cmax divided beta plus 1, and then inside the parentheses, I have basically 1 minus PT divided Cmax to the power of beta plus 1. And now I can say that the signs are correct. Okay, good. Now, let me go back to this relationship here. Okay? Because this one is the runoff. This one is the runoff. It's just the integral of the curve. Instead, if I want to compute the stored volume, I can write Wt is equal to, here you have a Pt minus the integral, and the result of the integral is here. So there is Pt minus Pt, and then, let me write it in order to be clear, Pt minus Pt plus, because there is a minus sign, and therefore the minus here becomes plus, Cmax divided beta plus 1, which multiplies 1 minus Pt divided Cmax beta plus 1. And then I can delete this, and therefore the expression for the volume stored in the catchment is this. Now, I don't rewrite it, and I remember it is correct, so this is fine. Now let me just make a consideration. What is this Wt? We introduced it very quickly. We said it's the volume of water stored in the catchment. Now, this brings back us to the symbol Wt, which has the same meaning in the linear reservoir. In the linear reservoir, Wt was the volume of water stored in the catchment. This is fine. And this explains to you why I had to change the variable when I turned to this representation. Because I wanted to keep Wt for the volume of water stored in the catchment. C is another story. C is the water storage which is varying into the catchment between 0 to Cmax. The potential water storage. So one thing is the water storage that is varying over the catchment. Another thing is the volume of water that is actually stored in the catchment. It's important to see the difference. And in order to better understand what the difference is, let's see what happens when the rainfall reaches Cmax, which means that the catchment is saturated. In this case, when the catchment is saturated, you get the maximum storage, the maximum Wt. So let's see what is the relationship between Wmax and Cmax. When Pt is equal to Cmax, this term here goes to 0, and therefore you get only Cmax divided beta plus 1. But then you may remember that beta is always greater than 0, which means that Wmax is always lower than Cmax unless beta is 0. If beta is 0, I already mentioned to you that we go back to a situation where you have uniform storage over the catchment. You go back to a situation that is similar to the linear reservoir that I had before there, and therefore you get that Wmax is equal to Cmax. But given that in general beta is greater than 0, you have a maximum storage in the catchment that is always lower maximum actual storage in the catchment that is always lower to the maximum possible storage in the catchment. Of course it is lower, because Cmax, you get it only in one point. In the other point of the catchment, you have a potential storage that is lower than Cmax. And therefore, your maximum water volume is a kind of average over the catchment and is lower than Cmax. So this is an important thing to clarify in your mind, the difference between this Cmax, which again is the maximum possible storage in the catchment that you get in only one point, and the maximum water storage. Oh, thank you. Thank you very much for that. And I'm sorry that you missed some. Thanks. This is my duty indeed, so maybe that we can promote you professor when you finish. Okay. At this stage, now the situation is still not clear to you, because at this stage you are able to compute the cumulative water storage in the catchment from the beginning of the event and the cumulative runoff. The cumulative runoff is given by this integral here, this one. But for us, it's not just important, it's important also, of course, we can manage with the cumulative runoff. But what is important for us usually is to compute the runoff not at a given time t and the cumulative one. We need to compute the instantaneous runoff, which means that we have to compute the incremental runoff between t and delta t. Meaning, let me better explain. We have to simulate an hydrograph, correct? And therefore, let me put the hydrograph here. I think, yes, I can delete this one. The hydrograph is given, for instance, by this curve, and therefore, if you compute the cumulative runoff up to here, you just computed this area. Which doesn't give you, at time t star, the actual value of Q. And this is the reason why I never used up to now the term, the symbol Q to denote the cumulative runoff. It's a different story. It's like rainfall. I wanted to reserve Q for the instantaneous river flow, or river flow at given time step. So basically now we are able to compute this area, but we are not interested in that area. We are interested in computing the cumulative runoff at this time t star, and then computing again the cumulative runoff at time t double star, and then of course if we take the difference between the two, which is given by this area here, what is this? It's the incremental volume of river flow that occurred between time t star and time t double star. If we divide this incremental volume of runoff by t double star minus t star, then we get instantaneous river flow. This is what we want to get. But actually this is simple, because you have here a relationship for the cumulative runoff. If you have hourly data, you can compute every hour this relationship. So you get an incremental curve, and by taking the differences, you get the values of this area here. It's easy. So let me now formalize it. And let me compute Q at time t. Or let's say Q at time t plus delta t. Where in your case delta t could be 1 hour. Okay, what is this? This is given by, in my slides, there are two different ways of computing it, of computing this incremental area here. In my slides, it's computed in this way. You take the rainfall at time t plus delta t, minus rainfall at time t, and this is cumulative rainfall, so you get the incremental rainfall, and you have to subtract the volume that is stored in the catchment. So minus W at time t plus delta t minus W at time t. This is a computation that you have to make, and this is now possible because you have the rainfall data and you have the W data. W data can be computed at whatever time by using this relationship here. Now we are done. Not completely, because indeed the model introduced a further complication. It introduces an assumption, because this is basically the runoff that is produced over the catchment, and then you have to route the runoff to the closure. What does it mean, route? River routing means transferring the local runoffs along the river network to the closure. Because, you know, if you think at the hypothesis, at the assumption that this model made, basically you get an estimate with Qt of runoff that is produced in several points over the catchment. You are interested in the river flow at the closure. So you have to transfer these components, these runoff productions, to the closure. So basically the model adopts a very simple way of transferring it. First of all, it assumes that the instantaneous runoff is split in two parts through a parameter alpha, which is included between 0 and 1. So you have Q at time t plus delta t, which is split in one component, which is 1 minus alpha Q times t plus delta t, and another one which is alpha Q times t plus delta t. And these are two components. Why two components? Because indeed, when the surface runoff moves to the closures of the catchment, usually you don't have only one process of river routing. You have at least you have several processes interacting. You have a fast transfer, at least, and a slow transfer. Because, you know, you have water that is flowing in the center of the river, and then you have water that is flowing in the sides, and then you have some water that goes, infiltrates a bit, and then comes back to the surface, and therefore it's convenient to split this routing process into components. Of course, you may say that the components could be 3, 4, or just one. This model, iMod, adopts two routing components. And how is the routing performed? Very simply, there is this slow component which enters a linear reservoir. And then you have your slow at time t to delta t at the closure. And here you have a constant k, s. This is a usual procedure that is adopted in hydrology. The routing, the slow routing, can be performed by using a linear reservoir, which is, be careful, it's not a linear rainfall runoff reservoir. It's a linear routing reservoir. It works in the same way as the linear reservoir rainfall runoff model, but conceptually it's a different story. Here you have not rainfall entering the reservoir. You have runoff production, slow runoff production that enters into the reservoir, and from the bottom discharge you have the river flow at the closure. This is for the slow component. The fast component adopts a very similar scheme, but the linear reservoirs are 3 in cascade. So let me depict them here. You have KF here,